Welcome to the course module of Communication Engineering. And in this video, we are going to learn about the classification of the random process. So far, I have already discussed about what is the random process. So in this video, we are going to see what are the various classifications. So let's begin this discussion. So basically, if we see the random processes, okay, then this is actually classified into these four categories. So first, random process is called as the stationary random process. And the second one is a non-stationary. Third one is the wide sense or weakly stationary process. And the last one is the ergodic random process. So let's try to understand what we mean to say a stationary random process. So normally I have already talked about the random process is actually a random variable which will be a function of time. So normally in the case of random process, we have a very large number of sample functions, and based on the sample functions, we are actually characterizing the random process. Okay, so based on the large number of sample function, we can calculate the statistical parameters of our random process. So normally, if we calculate the statistical characteristics such as mean square value, or any other higher order statistics, then if these parameters, if it do not change with the time, then normally the random process will be called as stationary random process. So the meaning is the statistical characteristics actually they are independent of time, right? So it will not be depending on time. So if statistical characteristics, whatever statistical characteristics we are calculating, if it is independent of time, then the random process will be called as a stationary random process. So here one thing that we have to understand, that if we talk about truly stationary random process, in that case, this random process should start from t equals to minus infinity, and it should go on forever. So it means that your random process, if it is denoted by xt, then it must be defined for t minus infinity to plus infinity, right? So in that case only, if it is defined for minus infinity to plus infinity, and its statistical characteristics are independent of time, then it will be called as ideally stationary random process, right? So here in practice, generally such conditions do not occur. Okay, we cannot have any such process that will start at minus infinity and it will go on forever. So normally in practice, the random process is considered stationary if there is no change in the signal generating mechanism. So you remember this point. This is a very crucial and very important point. There is no change in the signal generating mechanism. So at all the time, whenever you do the measurement for your random process under consideration, if this signal generating mechanism is not changing, in that case, we normally call the process as a random process, okay? A stationary random process. So normally in the practical sense, we generally talk about the strict sense stationary random process, okay? So it is a subclass of this stationary random process only. So normally in the strict sense stationary random process, if we do there is a, if we shift the time origin of our random process, then normally it will not impact the probability density function p x comma t. So as I already explained, that normally in the case of random process, the process will be defined, or it will be described by its probability density function. So if this probability density function is independent of time, then normally if you calculate px x comma t, then normally this will be equal to px x comma t2, or it will be also equals to px x comma t1. The meaning of this equation is that if we calculate the probability density function, first order probability density function, in that case this probability density function will be independent of time. At any point, if you calculate the probability density function, then all this probability density function will be same, right? It means that this px x comma t is same as pxx, right? It will be independent of time. Similarly, if we calculate the autocorrelation function, okay, if we calculate this autocorrelation function Rx T1 comma T2, then normally this autocorrelation function must depend on the difference between the T2 minus T1. So normally it will not depend on the individual values of T1 and T2. If this T2 minus T1, it will just only depending on the T2 minus T1, right? So if there are two locations, right? So normally, if this difference is constant, in that case, at anywhere in the entire random process, if you calculate this autocorrelation function, then this autocorrelation function will be a constant, or it will be just depending on this difference, right? So this is the mathematical equation that Rx T1 comma T2 will be depending on only to this particular T2 minus T1, the difference. Okay. So this can also be written as in this form. If we have this random process xt plus tau, if we calculating this autocorrelation, in that case, it will be only depending on this value of tau. Okay. So it will not be depending on at what instant of time, okay, we are calculating this autocorrelation function. It will not depend on the values of T1 and T2, right? So this is the meaning of your autocorrelation function, right? Which is depending on this difference only. Similarly, if we calculate the higher order joint PDFs, right? So normally these will also be independent of the choice of origin. And in that case, again, this PDF, if we calculate mathematically, if we calculating this PDF Px, x1, x2, xn, and then T1, T2 up to Tn, then this will be only depending on these differences, right? T1 minus T or T2 minus T or Tn minus T, right? So here we have defined the nth order PDF, right? So here we are interested in the nth order PDF. So normally this can also be equivalently written as this value will be equals to T1 minus T1 or T2 minus T1 or up to Tn minus T1, right? So here it will be again depending on the difference. Okay, it will be again depending on the differences at which this joint probability have been calculated. So it will not be depending on the choice of origin. So here you try to understand, here I am talking about the higher order joint PDFs. So if because here this joint PDF is being written for the actually it is a nth order joint PDF. So if this n is equals to infinity, then this will become a truly stationary random process. Okay, whatever I have shown here, okay, it is a true, if it is a truly stationary random process, in that case, this n should be tending toward infinity. So all other higher order statics will have this particular property, and that time it will become a stationary random process. Or otherwise, if these are the some properties, then it is normally called as the strict sense stationary random process. So let's try to understand this all mathematical discussion, okay, by this particular example. So if we consider this noise process, let us say we have this noise process. So normally if we calculate the mean of this particular noise process or at particular time instant t equals to ts. So if I want to know at t equals to ts, what will be the mean value of this particular noise process, then what I have to do is I have to take this, we have to sample it, and then we have to take this individual amplitudes of all the noise processes, and then we have to calculate the average based on the number of sample functions available in this noise process. So if in the case, if we calculating the mean value, and if this mean value doesn't depending on the time instant at which we are calculating this mean. So suppose if we are calculating the mean at this point, and if I want to calculate the mean at this point, and if this means are actually independent of time, if the mean calculated at t equals to ts, or you can say t equals to t1, and at another instant of time t equals to t2, if both are same, I can say that this mean is actually independent of time. So normally what happens, this will be independent for entire range of time t. Okay. So basically, whether you calculate the mean at this point, or any point, okay, in this particular range, this mean is going to be a constant. So if all the other higher order statistical characteristics are constant over the time, in that cases, the process is known as the stationary random process, right? So normally your noise process is actually stationary because its mean value and its mean square value is normally constant. Okay, it is independent of time, and therefore it is normally regarded as the stationary random process. But at the same time, if you take the example that I have taken several times to denote the temperature variation of a certain city on different days, then you can see that if I want to know what is the particular average temperature at a certain time, okay, if we calculate the average temperature at instant equals to T1, and if I want to calculate the average temperature at certain instant of time t equals to T2, so suppose it is at 11 a.m. and this is at 4 p.m. At that point of time, we know that this average value that we are calculating is not constant. Okay. And because this mean is not constant, I can say that it is a non-stationary process. So here we can say that this is the example, this variation of the temperature of a city is an example of a non-stationary process because its statistical characteristics is changing with the time, right? But here the noise process under consideration because its statistical parameters are not changing. Okay, and therefore we can say that it is a stationary process. Remember that it is not a truly stationary process. Okay, because only some of the higher order statistics will be constant over the time. Okay, so this is the meaning of stationary random process, and the same thing is actually being defined by these all mathematical expressions, right? So now try to understand the second one. Okay, so you see this non-stationary process, I have already explained. If its statistical characteristics is changing with the time, then obviously it will be called as the non-stationary process. Now we have to look at what is wide sense or weakly stationary process. So here what I will do is I will be just considering the first these two points. Okay, so if your stationary process is actually following this two relationship, right? So this is the conditions. So if the mean value of a wide sense stationary process will be independent of shift of time origin. Okay, so the meaning is the mean value will be a constant. So if we calculating the ensemble mean, in that case, this xt, the mean of this random process xt will be a constant. So if it is a constant, and if the autocorrelation function of a wide sense or weakly stationary random process will be also independent of shift of time origin, right? So you try to understand what does it mean by the shift of time origin. So if we do the time shifting of your random process, in that case, you won't be able to detect this shift of time origin into the this statistical parameter measurements. That measurement will remain constant, right? So here in the case of autocorrelation function also, this autocorrelation function will be only the function of this tau. Okay, it will be depending on the difference between the two time instant that we have taken, right? So it will be independent of what is the exact value of T2 and T1. It will be just depending on the difference of the two, right? So whenever this difference is the same, right, this will be the only function of your tau. Okay, and it will be a constant value normally. Okay, so here you can see uh, because here you can see this is your wide sense stationary process. So normally in the case of wide sense stationary process, these two conditions must be met, right? So the next one is our ergodic wide sense stationary process. So we have to understand what is ergodic wide sense stationary process. To understand this concept of ergodic wide sense stationary process, you try to again recall this. this particular variation of the temperature of a city. Okay, so we are having this sample functions. So here we can talk about at a particular instant of time, let us set it at 11 a.m. What is the average temperature over the particular month? Okay, so let us suppose that we are having such 30 sample functions in a particular month. Then I can ask you at a particular time, 11 a.m., what was the average temperature over the month, right? So that we can calculate by having the temperature value at 11 a.m. at this particular day, then again at this particular day, and then we have to calculate. We have to know first, we have to get all this data for all the days, and then we have to add all this temperature, and then we have to calculate the average. So while calculating such average, what we are doing is we are actually considering all the sample functions available in the ensemble. And therefore, calculation of such type of averages in which all the sample functions in the ensemble is considered is normally called as the ensemble average. Okay. Similarly, because it is a time varying function, right? So what we can do is we can also calculate the average value of this particular individual time functions, right? So this way we can define a time averages, right? So normally in the random process, we can either talk about the ensemble average, which considered all the sample functions, or we can only talk about a certain sample functions, right? So this way we can have the ensemble average or the time average. So here you can also understand from this graph. So let us suppose that we are having a random process, and this random process is having different sample functions. So let us say that we are having first sample function, this one, xt omega 1. This is the first sample function. Okay, and here we have the second sample function, right? This sample function is xt omega 2, and again I have this third sample function, xt omega 3. So here we have the three sample functions in this particular random process. So if you want to calculate what is the expected value of this random process, in that case, we have to consider all these three random process, and then we have to calculate its mean value, right? And here we can see that its mean value plot. Okay, so here is the mean value MT, and this is your ensemble average, obviously, because we are considering all the ensemble function in the ensemble, and therefore, if you plot this over the time, this mean is actually being changing in this fashion, right? So here you can see how you can correlate from the previous definition that I had taken. Okay, so from this definition we can see, because its mean is actually not constant over the time. Its mean is actually changing over the time, and therefore it is a example of a non-stationary random process. Okay, again you try to understand if we say that the autocorrelation function of the WSS process will be independent of shift of the time origin. So here you can see that if I take this a time instant to correlate the signal at let us say at T0 and T1, if we want to correlate the signal at this 2 point, then there is a certain difference between this T1 and T0, right? So if that difference is, let us say, of 1 millisecond, right? So the same difference I can take at some other point also. So it will not be depending on the instant of T1 and T0, but it will be only depending on the difference, the time difference between the two instants. So what I can do is I can take this another time instant T2 and this T3, and if the difference between the T3 and the T2 is again 1 millisecond, then whatever be the autocorrelation value that we have calculated in this case, in which the difference between the time instant was 1 millisecond, will be same as in this case. Okay, when this time locations have been changed, but the difference between the time locations are remain constant, which is equals to 1 millisecond, right? So now just to come back to this ergodic wide sense stationary process. So in the ergodic wide sense stationary process, what happens is normally we are having the ensemble average. Okay, I have already explained the what is the ensemble average. So for a random process, we can define the averages such as the mean, autocorrelation function, by considering all the sample functions that is ensemble, right? and therefore they are normally known as the ensemble average. And similarly, I can also calculate the average value of this entire graph, okay, because it is a time dependent function. So we can calculate over a certain range of time what will be the average value of this particular graph. So normally, if you only consider a certain sample function that time, if you calculate any average value, okay, whether it is a mean or it is a autocorrelation function or any other higher order statistics, then it is known as the time averages, right? So here you remember similarly, we can also define the averages for each sample function, right? Which is a function of time, right? And therefore they are called as the time averages. So normally, if we talk about the ergodic wide sense stationary process, then what happens for the first we have to see if we talk about the ergodic random process, then whatever be the ensemble averages that we are calculating, whether it is a first order statistic, second order, third order, if all possible ensemble averages for all other higher order statics, if it is its ensemble average, if it is equal to its corresponding time averages, right? If its ensemble average is equal to time averages, then the process is normally known as the ergodic random process. Okay, so there is a subclass which is your ergodic wide sense stationary process, right? So first of all, if all possible ensemble averages are equal to corresponding time averages, then it is called as the ergodic random process. But if it's mean value, if we calculating the ensemble mean and if we calculating the time mean value, okay, if mean and its autocorrelation functions, if its ensemble averages will be equals to time averages, in the case of mean and autocorrelation function, then normally it is called as the ergodic wide sense stationary process. Okay, so here we can see the mean value that we can calculate. So the ensemble averages, this is denoting you the ensemble average at the left hand side. This is the random process xt. We are calculating the its mean value that must be equal to one of the uh, time average of your sample function. Okay, so we are just considering that one of this sample function whose time average we are actually calculating. So whenever this ensemble average is equals to time average, okay, so we are here we are just talking about the mean value. In that case, it will be ergodic process, right? So ergodic wide sense process. So normally here you can see this. This time average will be calculated by having this particular equation that I have already discussed in my previous lecture. So this ensemble average can be calculated by following this integration in which we have to have this particular value of your probability density function, right? So we must need a probability density function to calculate the ensemble average, and we have to follow this particular equation. But if we wish to calculate the time average, okay, xt, that value will be calculated by having this particular equation. So here you see, here we'll be having the uh, time dependent function, right, xt. So this will be a particular your sample function, okay? So that sample function has to be integrated over a particular instant of time, right? So this way we can actually calculate your time average, and this will be denoting you the ensemble average. Similarly, if you see the autocorrelation function, so here if this autocorrelation function for your ensemble, if it is equals to the time average autocorrelation function, in that case, if this mean and autocorrelation function follows these two properties, okay, then it is normally referred as the ergodic wide sense stationary. Okay, so you try to understand this difference. Okay, in the ergodic random process is the bigger class, and this is one is the subclass, right? So in the ergodic random process, all possible ensemble averages will be equals to time averages. But in the case of ergodic wide sense stationary process, this mean and autocorrelation ensemble averages and time averages should be equal. Okay, so here you can see this ensemble autocorrelation function can be calculated by having this particular equation xt1 into xt2, and we have to calculate this average, right? But at the same time, if we want to calculate the time autocorrelation function, Rx tau. Okay, so that can be calculated by having this particular integration, right? So over a particular instant of time, we have to calculate this particular integration, right? So this way, we can calculate the time average, right? So here it is very important to know that the ergodic random process or ergodic wide sensor stationary process, it is a quite important class of your random process. So what does it mean by having this equation is that, so normally to classify a particular random process, what we need to have is we need to have a very huge number of sample functions. So if we talk about ideally, what we require is we require to have the infinite number of sample functions, and thereby we will be able to characterize this particular random process, and we can calculate what will be the all other higher order joint PDFs, right? And this way we can calculate its statistical characteristics. So at that point of time, what we need is we need to have a very huge number of or large number of sample functions, right? So, but suppose if a random process is known to be ergodic, then we don't require very large number of sample functions. So you must be wondered why it is not required, because we know that even if we have one sample function, then that sample function time average will be equal to the ensemble average. This is the beauty of this particular ergodic random process that you remember. Okay, so in the case of if it is known that the random process is ergodic, then in that case, if you have one sample function, then if you calculate any average value, that average value will be directly equal to its ensemble average. And in that case is you don't require the huge number of sample function. So that is the very important point of your ergodic random process. Okay. So now we'll try to understand one problem. Okay, whatever I have discussed. So we'll try to understand this problem that we have to show that the random process defined by this analytical expression xt equals to a cos omega ct plus theta, where theta is a random variable which is uniformly distributed in the range of 0 to 2 pi, is a wide sense stationary process. Okay, so we have to prove that this particular process is a wide sense stationary process. So you recall the wide sense stationary process means we should have its mean value, its ensemble mean value should be a constant value, and its ensemble autocorrelation function should only depend on the time difference. Okay, so that we have to prove here, right? So let us try to see, let us try to plot this one. So if we have this random process, so because theta is a random variable and it is uniformly distributed over 0 to 2 pi, so for the various values of theta, we can plot infinite number of such cosine functions with the different phase values, right? So here you can see if we change the phase values, we are going to get different cosine functions, okay, with a different phase value, initial phase values, right? So this way we can have the infinite number of such samples, right? And therefore it is a random process, right? So now what we can do is we can try to calculate what will be the mean value of this random process. To calculate the mean, if we do this calculation, right, because a is a constant, okay, so this a will be out of this mean, okay, out of this bar. Okay, so we can calculate, if we calculate a into cos omega ct plus theta, then we have to calculate the mean value due to this random variable theta. Okay, so because just I have explained you the formula. Okay, because we know that here this theta is a random variable. Okay, so if we able to calculate this particular mean, then we will be able to calculate the mean of your random process xt. So here again, I'm using the same formula that we have to integrate it over a certain range of the random variable in which it is defined, and we have to take the value x, then we have to define its probability density function, right? So here the random variable is actually your cos omega ct plus theta, multiplied with the probability density function of your random variable theta. Okay. And because this random variable theta was defined from 0 to 2 pi, okay, so therefore this integration must go over from 0 to 2 pi. So this way we have to do this integration, and we must know the probability density function for this particular range of your theta 0 to 2 pi. There will be a uniform distribution, and we know that the area under the PDF curve must be unity. So this value p theta, this particular probability density function for random variable theta will be equals to 1 by 2 pi over this range 0 to 2 pi, and it will be 0 outside this range. Fine. So if you substitute this value of this PDF value, then you will be able to show that this particular mean value, okay, this will become 0, because if you integrate the cos function, okay, over a certain range 0 to 2 theta, this value is going to be 0, right? This average value is going to be 0. So it means that this mean, whatever we are calculating for the random process, is actually 0, which is nothing but a constant value. So here, the first thing that the requirement we have already proved, that this ensemble should have the mean as a constant value. Okay, so this ensemble mean is a constant, right? Now we try to prove the second property. We have to calculate the autocorrelation function of the random process. So here you can see we can take this equation like x t1 multiplied with the x t2, and then we have to calculate the mean. Okay. So if you take this random process xt, and if you substitute t1 multiplied with the a cos omega c t2 plus theta, then this a multiplied with the a will become a square, and then we will be having this two cosine functions, right? At time instant t1 and time instant t2. And then because a square will be a constant value, it should become out of this bar. And then we can calculate this particular function, right? So you can just use the a formula for your cosine functions, right? And that time it can be converted into cos a minus b plus cos a plus b formula, right? And this way we can split it, and then we can use the condition that if we have these two functions a plus b bar, then that value will be equals to a bar plus b bar. Okay. So this way, if you solve this particular expressions, okay, then you will be able to show that this results. Okay, if you want to calculate, you will be able to show that this result is going to be equals to 0, right? So this integration, again, we have to this average value we have to again calculate, okay, over the 0 to 2 pi range. So if you do this calculation, you will be able to show that if you perform this integration, okay, this integration is again going to be 0. So you remember here again, this is variable theta, which is your random variable. So again, we have to use that equation x multiplied with the probability density function. So there we have to multiply the probability density function again equals to 1 upon 2 pi. So therefore we are getting this value 1 upon 2 pi. Okay. So again, if you calculate this integration, this value is going to be 0, right? So here you can see this particular second term, the mean value of this particular second term is going to be 0. Okay. And we are just left with this particular integration, this particular mean value, right? So here we can see because we are having a definite values of t2 and t1, and therefore it will be also treated as a constant, right? So the ultimate result that we are going to get is rx t1 comma t2, and this value will be a square by 2 cos omega c t2 minus t1. So this value will be your, this is the actually final value of your autocorrelation function. So that we can see here that this autocorrelation function is ultimately depending on the difference of t2 minus t1, right? It will be only the function of t2 minus t1, right? So this way we have to show that the autocorrelation function is the only function of the difference of this two time instant t2 and t2 and t1 and t2, and therefore it is also satisfying the second condition of your WSS stationary process. Okay, so therefore we can say that because this random process is actually having a constant mean and its autocorrelation function is the only function of tau, therefore we can say that the given random process is a wide sense stationary process, right? So I hope you must have understood something. Okay. So now we stop here today in this lecture, and we will discuss some other topics in my next lecture. So thank you for watching this video. If you have any query, let me know with your comments. Thank you.